All right, so now we're going to take a look at some of the properties, the acidic and basic properties of different salt solutions. So as a reminder, right, salt is a general name that we give to an ionic compound that is formed from the reaction of an acid and a base. Okay, and salts generally are strong electrolytes. Right, and what that means is that in aqueous solution, they will dissociate completely into ions. That's the assumption that we're making when we look at this section. So dissociate completely into ions in aqueous solution, meaning when dissolved in water. So when we talk about salt hydrolysis, right? So the hydrolysis of a salt, and again, a salt is just an ionic compound. That is a process whereby those ions that are produced when it dissolves in water, those react with the water to produce either hydroxide ions, so the OH minus, or the hydronium ions, H3O plus. So obviously now, if the salt hydrolysis leads to the formation of hydroxide ions, that would make that salt solution basic. Whereas if it leads to the formation of hydronium ions, it would make that salt solution acidic. Right? So what will dictate whether it forms one versus the other? Well, if we take a look at, first of all, our basic salt solutions, our basic salts would contain the conjugates of weak acids. Okay, so remember now, a weak acid is going to have a strong conjugate base. So for example, if you have a weak acid like HF, right, this is a weak acid. The conjugate base of this would be F minus, right? That's the conjugate base, and that's going to be a strong conjugate base. That F minus obviously could come from the weak acid, or this F minus could come from a salt. Like, let's just say sodium fluoride, right? So sodium fluoride, ionic compound, in solution, this will dissociate to give you Na plus and F minus, right? So this F minus, the fluoride, that would come from a salt, and it's the conjugate base of a weak acid. It will react in aqueous solution. It will grab a hold of a proton from the H2O to form HF, and then we get a bunch of hydroxide. As a result, this is going to be a basic salt and a basic solution. So generally, an anion, that is the conjugate base of a weak acid, is going to react with water to produce hydroxide, right? So we can generalize that. An anion of an anion, that is the conjugate base, sorry. Of a weak acid reacts with water to produce the hydroxide. Okay, and as a result, that is going to lead to a basic salt solution. We can also calculate the pH of that basic salt solution the same way that we can calculate the the pH of any weak base solution by using the Kb value for that anion. So let's take a look at an example of that. So we have here, calculate the pH of a 0.1 molar solution of sodium hypochlorite at 25 degrees Celsius, right? So first thing, what is this? NaOCl. Well, that's a salt, right? You see, that's an ionic compound, first of all, because you see a metal in there. And this contains, in solution, this will form the Na plus, and you have the C or the OCl minus, right? The hypochlorite ion. And this is the conjugate base of the weak acid, which is HOCl, right? To get the conjugate, or to get the corresponding weak acid, we just stuck an H plus onto it. So what we can do is we can look up the Ka value for this. Okay, so that is equal to 3.5 times 10 to the minus 8. That's the Ka. So what we can do then is compute the Kb value for the corresponding conjugate base, for the OCl minus, by using the technique we talked about before. So you're going to use Kw is equal to Ka times Kb, and we can use it here because both of these two things are conjugate acid-base pairs. So the Kb would be equal to Kw divided by the Ka. So that would be 1.0 times 10 to the minus 14 divided by the 3.5 times 10 to the minus 8. So the Kb then would be equal to 2.9 times 10 to the minus 7. And that is for the OCl minus. And we can then go ahead and stick that into our ICE table, or use our ICE table to compute that, right? So we have our OCl minus plus H2O reversibly to produce HOCl plus OH minus. Initial change, constant and equilibrium. Okay, ignore the H2O. If we have our Kb value, we can use that then in conjunction with the ICE table. So let's see, are we given? Yeah, we're given a 0.10 molar solution of the sodium hypochlorite, right? So in aqueous solution, right, when this dissolves, this is all going to dissolve in a 1:1:1 mole ratio. So the concentration of this will be the same concentration of the hypochlorite ion. So we have 0.10 to start with, and we have none of these. Stoichiometry dictates we're going to gain X in each of these. We're going to lose X over here. So at equilibrium, 0.10 minus X for the reactant, X for the products. We can write our Kb expression for this. That is X squared then divided by 0.10 minus X, and that is equal to the Kb value we calculated, which was 2.9 times 10 to the minus 7. Okay, and we're going to assume X is small. Okay, so then this becomes X squared over 0.10 equals 2.9 times 10 to the minus 7. We solve for X, and X here is going to be equal to, let's see. Oh, there it is. X there is going to be equal to 1.7 times 10 to the minus 4 molar. So let's check the approximation. So we have the 1.7 times 10 to the minus 4. We divide that by the original concentration, which was 0.10 times 100. Okay, and that is equal to, let's see. So that gives us 0.17%. Okay, so that is X, I'm sorry, it's less than it's less than 5%, so that our approximation is valid. All right, so we have X equals 1.7 times 10 to the minus 4. What is X equal to? Well, X is the concentration of the hydroxide. So 1.7 times 10 to the minus 4. So we can calculate the pOH for this. So the negative log of 1.7. And that gives the pOH as 3.77, which means the pH then would be equal to 14 minus 3.77. And that gives a pH of 10.23. Okay. That makes sense. The pH is a basic pH, and we predicted that this here being the salt or the salt containing the conjugate base of a weak acid should be a basic salt solution. So that is the case for basic salt solutions. If we take a look at acidic salt solutions, so before we get to an example, let's just write a couple things out. So for acidic salt solution, so you can maybe guess what can lead to what types of salts will be acidic. So when the cation of a salt is the conjugate acid of a weak base, the solution of the salt will be acidic. So the salt solution will be acidic. So it's important that you take a look at the salt itself and try to identify the different ions that are there. So for example, we have a calculated pH of a 0.10 molar solution of ammonium chloride. All right, so we're given ammonium chloride, NH4Cl, concentration as 0.10 molar. This ammonium chloride, okay, that is an ionic compound because it has the ammonium ion, the chloride ion. This is a salt. It will dissociate completely to give you an H4 plus, and then we're also going to get Cl minus, right? So you'll notice a couple things here. The anion, Cl minus, is actually the conjugate base of a strong acid. Okay, this is the conjugate base of a strong acid. So this will generally not have any effect on the acidity of the solution. However, we do have the cation here, the ammonium ion, and this cation is the conjugate acid of, if we take away an H plus, we will get the base, the conjugate base of NH3, ammonia, right? NH3 is a weak base. So the conjugate acid of a weak base is actually a strong acid in comparison. So what we can do is something very similar. We can write out the equation for this acid. So we have our ammonium ion, the NH4 plus, in H2O, equilibrium arrow. We're going to get our NH3. And then we're also going to get our H3O plus concentration. We have our ice table that we can generate. Okay, ignore water for right now. We're given the concentration of the ammonium chloride as 0.10 molar. Remember now, your salts dissociate completely, so that will also be, and they dissociate in a 1-to-1 mole ratio. That will also be the concentration of the ammonium ion. We have none of these to begin with. We're going to gain X along the way. We're going to lose X here. So at equilibrium, we have 0.10 minus X. We have X and X on the other side. So we know, or we can look up the Kb value for NH3, right? Because that's the conjugate base, and that is equal to the Kb value for NH3 is, let me check my table. That is equal to 1.8 times 10 to the negative 5. Which means we can find the Ka for NH4 plus. We'll take the Kw, 1.0 times 10 to the negative 14 divided by the Kb value for the conjugate base, which we just looked up. So we get the Ka for ammonium, the ammonium ion, as being equal to 5.6 times 10 to the negative 10. So I know what that value is. I can write my expression down here now. So Ka would be equal to the NH3 concentration times H3O plus divided by the NH4 plus, and that is equal to 5.6 times 10 to the minus 10. Substitute my values. I have x squared over 0.10 minus x. That's equal to 5.6 times 10 to the minus 10. I'm going to assume x is small again. That's my assumption. Okay, so it simplifies the calculation. I end up with x squared over 0.10 is equal to 5.6 times 10 to the minus 10. I solve for x. X ends up being 7.5 times 10 to the minus 6. Okay, and then we want to check the approximation. Okay, and I'm not going to go through that. I think that's something you can do. And we'll see that it is valid. So our x there is equal to 7.5 times 10 to the 6. That is the concentration of the H3O plus. So then we find the pH. We just take the negative log of the H3O plus. And that gives us a pH of 5.12. That's an acidic pH. That makes sense, right? Because we said at the beginning, when the cation of a salt is a conjugate acid of a weak base, that salt solution will be acidic, and we've just confirmed that it is. So there are other situations, another important situation where, or that can lead to a solution, a salt solution being acidic. And that is if you have a small, highly charged metal ion. These can react with the water to produce an acidic solution. These small, highly charged metal ions typically include ions like aluminum, so the Al3 plus, the chromium ion, C with the 3 plus charge, iron, Fe with a 3 plus charge, bismuth, Bi, the 3 plus charge, and also beryllium, the 2 plus. So they're small ions and they're charged, have high charge associated with them. And what that does is it causes these to actually bond with water molecules, and it leads to an increase in the polarity of the OH bond in water, which allows that hydrogen atoms, or the hydrogen atoms in the H2O, give them a greater tendency to ionize than those in the water molecules that are not associated with the highly charged metal ion. So this is another example where we can have an acidic solution forming due to having these small, highly charged metal ions in the solution. So we've seen examples of basic solutions, basic salt solutions, acidic salt solutions. What about neutral salt solutions? So we've just seen that the small, highly charged metal ions can lead to the formation of acidic salt solutions. However, what we're going to see is that the metal ions that belong, or most metal cations, of the groups 1 and group 2 do not impact the pH of a solution. What we're also going to see is that anions that are the conjugate bases of strong acids do not hydrolyze to any significant degree. In other words, they won't affect the pH of the solution, right? And we talked about this as a consequence of that inverse relationship where you have a strong acid, you have a weak conjugate base, for instance. So if you have significant degree, so if you have a salt such as NaCl, right? What are the ions that we have present? Well, we have Na plus and we have Cl minus, right? The Na plus is a group 1 metal ion, so no effect on the pH. And the Cl minus, this is the conjugate base of a strong acid. The strong acid there is just add an H plus onto it, it's hydrochloric acid. So this is also have no effect on the pH. So as a result, a salt solution of sodium chloride, table salt, will actually be neutral. So we can summarize those effects, and your book does a good job of summarizing in tabular form the pH of salt solutions that we can qualitatively predict by the ions that are present. So this means that you need to be able to approach or to take a look at the formula for a salt or an ionic compound, determine the ions that are present, and that will then dictate the acidity or the basicity of that salt solution. So a cation that will make the solution acidic will be the conjugate acid of a weak base, right? We looked at those examples before. And then we also have seen these small, so tiny ions that have high charges on them other than the group 1 and group 2. So aluminum, chromium, iron, bismuth are the most common ones. These lead to acidic solutions. Basic solutions can be produced from anions that are the conjugate bases of weak acids. Okay, so the cyanide, NO2. This should be NO2 with a minus charge. That's a typo. NO2, oops. NO2 with a -1 charge. Acetate ion, for instance. And then we have the cations that will not affect the pH of a solution. So the group 1A or the group 2A cations, lithium, sodium, barium, etc. And then anions that will not affect the pH would be the conjugate bases of strong acids. So chloride, nitrate, perchlorate, etc. All right, let's take a look at an example of this. And we'll do, let's do the KNO2 example. So we have potassium nitrite. So what are the ions? Well, we have the K plus and we have the nitrite ion, NO2 minus. Okay, so this is a group 1 metal ion. Cation. And that will not have an effect, so no effect on the pH. The NO2 minus, right, this is the conjugate base of HNO2 minus, or HNO2, nitrous acid, and NO2 is, I'm sorry, HNO2 is a weak acid. So this will actually ionize in solution. So we have NO2 minus, right? We will get the H NO2, and then we'll get the hydroxide. So this will then lead to basic salt solution, right? So this here will be basic. The other component, the potassium ion has no effect. So overall, we can say that solution, that salt solution is going to be basic. So if you have a salt where one component of the salt doesn't affect the pH, but the other one does, well, then the pH of that solution will be determined by that component that does affect the pH of the solution. But what about if you have a salt where both the cation and the anion are able to hydrolyze in solution? Well, what we're going to have to do is to compare now the Kb and the Ka values for the respective conjugate acid-base pairs in that system. So even though how we calculate the pH in systems like these can be quite complex, we can still make some qualitative predictions regarding the pH using the Kb of the anion in the salt and the Ka of the cation of the salt. So for example, if the Kb is greater than the Ka, we can say that the solution is going to be basic. If the Kb is less than the Ka or the Ka is greater than the Kb, then the solution is going to be acidic. And if they're nearly equal to each other, then it's going to be a neutral solution. So for example, if we have something like ammonium nitrite, so NH4NO2, okay, what are the ions here? Well, we have the NH4 plus, and we have the NO2 minus, right? This is the ammonium ion. And then this is the nitrite ion. The ammonium ion is the conjugate acid of a weak base. So it will have, so conjugate acid of a weak base. Okay, so this will have some acidic nature to it. The nitrite ion, as we saw previously, is the conjugate base of a weak acid. Okay, so then this then would contribute some basic character to the solution, which is going to win out. Well, this is where we are going to now compare the Ka and the Kb values. So the Ka for NH4 plus is 5.6 times 10 to the negative 10. The Kb for NO2 minus is 2.2 times 10 to the negative 11, right? So we compare these two values, which one's larger? Well, to compare them, just look at your exponents, right? If it's a negative exponent, the smaller the negative exponent, the larger that thing is. So this here is going to be larger. And because this is going to give some the acidic nature to the solution, this is going to win out. So overall, we can say then that this solution is going to be acidic, right? Because the Ka is larger than the Kb value. So overall acidic, maybe just slightly acidic because there's not that much difference between them, but they are different, right? And maybe a 1 order of magnitude difference. So if you have a situation where both the cation and the anion can hydrolyze, you can compare the Ka and the Kb values for the cation and the anion of the salt respectively.